Okay, thank you very much for inviting me to give this talk. It's a real privilege to be talking at CompFlu again. Let me share my screen. So here's what I'm going to tell you about motile particles in slightly more complicated media. These are my sources of support. I'll introduce the topic and I'll tell you first about some background about particles moving through a fluid monolayer actually of beads, and then a crystalline layer. I'll give you results in each case and then summarize about why these results might be interesting. It's probably unnecessary, but I better at least briefly define active particles. Active particles are powered. They could be living or artificial. They break details. The active systems break detail balance at the level of the component particles because each particle takes up free energy, turns it into work. The steady state of these systems is not time reversal invariant. Collections of such particles are called active matters, and there's lots of reviews and perspectives, including one very recent one, which you might find interesting. An aspect which particularly interests me of late is that of non-reciprocal interactions. By non-reciprocal, I mean that you have two objects, like two people or two particles, and one, let us say, is drawn to the other, and the other runs away from the first one. In ordinary life, this kind of thing happens very often. In fact, even the flocking interaction among locusts, it turns out, is based on such an interaction where a locust behind tries to pursue the locust in front and capture it, and because it wants to eat it, and the locust in front tries to run away from the locust at the back. There are many situations in the living world, including in neural nets, where this kind of non-mutual or non-reciprocal interaction is abundantly observed. In this talk, I'll tell you about the emergence of non-reciprocal interactions in a purely mechanical system of motile particles moving through a dense layer of non-motile particles. A fluid layer kind of in which the interaction in a sense is hydrodynamic, and a crystalline layer in which the interaction is mediated by something resembling elastic strains in that layer. And non-reciprocality, you will see, emerges in these situations. Let's first review the dynamics of motile particles moving through a fluid layer, not a conventional fluid, but a fluid layer of beads. There were these experiments which were part of Nitin Kumar's thesis. Nitin is now on the faculty at IIT Bombay. He was looking at particles of this sort. You're looking at a top view of the system. It's a horizontal layer that's being vibrated vertically. The layer contains a bunch of beads, and it contains one elongated tapered particle. That particle takes up the vibrational energy and turns it into horizontal motion and pushes the beads out of the way as it moves. So Nitin and Harsoni and Ajay Sood and I looked at collections of such rods and showed that you can actually have a flocking phase transition. Here, let me specialize or simplify from that to a one-particle case. So imagine you have one particle whose position is R, which has an orientation N, and moves in the direction of that orientation with a speed V0. Let the bead medium be characterized, because it's a fluid, let the bead medium be characterized by a velocity field V. That velocity field can get damped by the substrate. It can lose momentum laterally to other particles in the medium. The single motile particle pushing its way through the medium gives you a localized point force in the direction in which this particle is pointing, and with a magnitude, some magnitude F. And then there's a pressure. In the simplest case, you could take this layer of beads to be effectively incompressible, and this pressure just enforces that incompressibility. The orientation of this motile particle can change. In the case of a fluid layer of beads, it can change either by reorienting parallel to the velocity or by being reoriented by gradients of the velocity. We'll see exactly what I mean by this in a couple of slides. This is a very schematic rendition of the more complicated equation of motion. So in pictures, what I mean here is the following. That imagine you had this one particle moving not through this crystalline layer, but through a fluid layer, then as that particle moves, you can measure the velocity field of the other particles in the medium. And you find that you produce a circulation. So near this particle, you have a flow of beads in the same direction, far away a flow that circulates. The distance out to which this velocity field decays gets bigger and bigger as the layer of beads is increased in density. If you put a second particle in the presence of this one, then the bead flow here going at this particle will reorient it to point parallel to this one. That's equally true if this other particle is some distance away, but not immediately on the side, but say behind. Okay? You've got a non-uniform drag on this particle because its shape is non-uniform in thickness. You have flow at the medium, at the particle due to the beads, and that reorients it. Very much like a wind reorients a weathercock to point in its direction. So you get an aligning interaction. On the other hand, if the neighboring particle is sitting in the vortex, it gets rotated and turns away. So now if you have two particles, each experiencing the vorticity of the other, they'll turn away from each other and they'll effectively repel. So these are the behaviors you expect in a fluid medium. Now, as you increase the bead packing fraction and make the bead layer crystalline, here illustrated by numerical measurements of the hexatic order parameter, which at high enough area fraction of beads becomes long-ranged, and here illustrated by the rigidity of the bead layer, on which we performed a single particle microrheology experiment, both in the simulations and the experiments. You see a clear onset of elastic rigidity. So as you increase the bead monolayer packing, you get a crystalline state. That crystalline state looks instantaneously like this. And whereas in the fluid layer, a single rod moving along drags the beads like this, in the crystalline layer, the single particle moving along basically leaves the few marked beads here behind, and it does something else in the medium. So the question is what? Basically, the moving particle in the bead monolayer doesn't produce the kind of large-scale fluid flow I showed you a few slides ago. What does it do? Well, we need a theory. Now, active particles in an elastic medium have been studied in various forms: force dipoles without motility, motile particles but without the reorienting interaction. We decided to study motile particles in an elastic medium in which the motile particle forces the medium and the medium acts back on the particle. So this is what Rahul Gupta did for his PhD work, along with Harsh Soni, who was then a postdoc with us, and Roshan did experiments in Ajay's lab. So the theory of a motile particle in an elastic medium looks like this. You've got a particle, it has position R, orientation N. The medium is described by a displacement field U, governed by an elastic free energy F with elastic constants. There's friction zeta with the base, that's all we'll worry about. And so you get an equation of motion where the particle moves in the direction it's pointing in. The particle forces the bead medium, as I showed you in the earlier part of the fluid. The medium reaches a compromise between forcing by the active particle and relaxation to minimize the free energy. And it has a dynamics governed by damping with the substrate. So frictional forces are balanced with elastic forces and active forces. The strains in the medium reorient the polar active particle, either by saying that the particle should align along the principal axis of the strain, or the particle at higher order gradients can point in a direction determined by the curvature of the crystal planes or lines. So if you take this equation seriously, let's look at this one. Let's first say, supposing you have one active particle. Let's not worry about reorientation because you have only one particle. Let's see how the medium responds to that one particle. Let's co-move with this one particle, So in its own reference frame, what will happen is that this du over dt will simply become of a directional derivative in the direction in which the particle is moving. And you'll solve for the displacement field in the medium with this rather interesting equation, whose solutions turn out to be modified Bessel functions. The really interesting thing about those modified Bessel functions is that if you look in front of the particle, the decay is highly screened exponentially. If you take the same expression and look for negative values of the coordinate, it turns out it decays only as x to the minus half. So you've got this moving particle, and its strain field is highly screened in front of it, but decays very slowly behind it. What are the consequences? The consequences, first of all, are a displacement field with a very distinctive form, which you can measure in computer experiments, which Rahul Gupta did. In particular, he showed that this very slow decay, x to the minus half behind the particle, is beautifully evidenced by the actual measurements, as are many, many qualitative and quantitative features of the displacement field. Now, if you put two particles together, and let's say you put one particle in the strain field with the other, if you align if the one particle is allowed to align with the principal axis of the strains produced by the other, the two particles attract. These ideas were tested in experiments in this now well-known vibrating layer geometry, where you put the particle into this little gap, and the particle is motile because when it lands, static friction at the base impels it along its length. What we found was that in the crystalline system, two particles seek each other out and attract each other, just as the theory predicted. Whereas when the medium is fluid, as I showed you earlier, they turn away from each other, as seen in these pictures. These were the experiments, these were the simulations. If you then put two particles together and now solve for the complete dynamics of a pair of particles theoretically, you get this rather intriguing behavior where, because of the fore-aft asymmetry in the screening, you can have one particle sneaking up on another like this, as seen here in detailed theoretical calculation, here in simulations, and here in experiments. And just to show that it really does happen, here's what happens. The particle at the front has no idea the particle at the back is sneaking up on it. The particle at the back can see the strain field of the particle in front. So you can see that. You see that in the computer recreation of these experiments as well, rather dramatically. So what we've shown is that you can build a detailed theory of particles forcing their way through an elastic medium. The effect of these particles on each other is through the strain field of the medium. They sense, the particles sense the strain field and respond to it by reorienting. That interaction is non-reciprocal. What particle A feels due to particle B and what particle B feels due to particle A are very different. And you can actually get pursuit and capture behavior, as I showed you here. To summarize, elastic interactions of active polar particles are naturally non-reciprocal. We made a detailed theory of the pair interaction. We found experimental and simulational evidence for it, for the form of the strain field, for the non-reciprocal capture. If you put in many particles, rather dramatic things happen, which I'll just show you in this teaser of a movie, where you can see they seek each other out in a totally non-potential manner. All I can say about this beyond that is that surely nature uses this somewhere. Maybe motile cells in the epithelium, maybe cells crawling through the extracellular matrix. We don't know, but it seems like too nice an idea not to use. And with that, I'll stop sharing and close my talk. You can read about this in this preprint, which is still on the archive.